残酷な天使のように少年よ神話になれ未来目指すための羽があること残酷な天使の手で窓辺からやがて飛び立つほとばしる熱いパトスで思い出を裏切るならこの空を抱いて輝く少年よ神話になれ
With the uptake of automation in the industry, we've seen an increased use of robotic arms for simple, repeatable actions, or conversely, highly specialized tasks. Controllers have been played with, which allow for a user to map desired movements to the robot in real time. However, for more complex or dangerous tasks, an operator is still required, which increases the risk for human life. As well, these solutions often don't allow for the user to actively feel what they are grasping. For haptic technologies, these are primarily in the virtual reality industry. However, as the name suggests, there isn't any tangibility in the virtual space. After successfully making 2 gloves for 2 hands, our team has decided to make a glove, which can control a robot hand to control said gloves. Our team has developed the Bionic Interface Tracking Controller, a haptic experience system with the goal of designing a safe, versatile, and easy-to-use device to dexterously manipulate objects from a distance. This would take the form of a wearable glove, which tracks the finger and hand movements of the user and controls not only a multi-degree of freedom arm, but also a robotic hand, which relays the sensation of grasping an object.
On the user end, the controller glove comes as a 2-part system. 3D printed from PA12 nylon, the custom surface modeled shell allows it to be lightweight and stronger than other printed plastics on the market. Through the polycarbonate cover, our PCB is mounted close to the hand to provide accurate orientation tracking. Running from each finger are 2 Kevlar tension lines, one tracking the fingertip and one at the first knuckle providing 2 degrees of freedom. Each tension line is connected to 3D printed sheaths at their ends and runs to one of 9 servo motors, located on the forearm to offload weight. Initially designed for a fingerless glove setup, the fingertip sheaths were made to mold to a user's hand, providing a tight but comfortable fit. After complications with the tension lines wandering off path, we opted to shift to a fully covered glove, proving to be a more flexible option, ironically.
The end-of-arm tool was designed as closely as possible to the experience of a human hand. To size the device, under-actuated 4-bar linkage assemblies and the average finger dimensions of Turkish male dentistry students were taken and then drafted in SOLIDWORKS. Each finger is powered by 2 Actuonics linear actuators, allowing the joints to mirror the movements of the controller glove. The palm enclosure, much like the user-controlled end, is 3D printed and made out of lightweight nylon. Encasing all of the electronics is a flexible resin shell, providing a durable and grippy surface allowing you to do whatever a realistic hand can do via being teleoperated from a distance. Touching, picking, placing, squeezing, rotating, pushing, lifting, and many more interactions are now possible. Furthermore, the adapter conforms to ISO standards, allowing the end-of-arm tool to be mounted to any typical 6-axis robot found in the industrial market.
In terms of electronics, boom! They're all on board on the hand.
Powered by USB-C and an external 6-volt power source, our custom double-sided PCB minimizes the form factor to fit comfortably on the hand. The brains of the operation is the ESP32, allowing the glove and end-of-arm tool to communicate wirelessly over the ESP-NOW protocol. This allows for the system to communicate with down to 1 millisecond latency. It's not perfect, but we already knew your skill issue wasn't due to your 90 millisecond ping. So what does the control system look like? Our IMU tracks user motion, and we convert acceleration into position. Finger curling pulls tension lines connected to the servo motors, which is then mapped to linear actuators on the end-of-arm tool. Force-sensitive resistors detect when the robot fingers grip an object, which then tells the servo motors to lock rotation, and combined with vibration motors, gives a tactile haptic experience of holding something in thin air. Finally, mounted atop the forearm enclosure is a human-machine interface, which allows users to track statistics and calibrate the system.
In order to control a robot, we need three main functionalities: kinematics, trajectory planning, and optionally feedback control. In our project, we implemented these in the space of dual quaternions, which provide a minimal, fast approach to screw transformations. We implemented forward kinematics by simply chaining the relative dual quaternions of the robot joints. Inverse kinematics were implemented with the intention of being compatible with any PR robot. As such, heuristic and numerical approaches using the Jacobian matrix were favored. For forward trajectories, we used screw linear interpolation, which allowed us to drive every joint with a single time parameter. Backwards trajectories were implemented, but the implementations were too slow for teleoperation. We approximated them with high-frequency inverse kinematics. A robot visualization was also developed, using OpenGL in order to demonstrate our control algorithms. The basic viewer generates an abstract model from a Dynavit-Hartenberg table. More realistic visualizations, with actual robot models, have to be rigged up manually. There is room for improvement in automating this process.
So, what's the future of this project? Our method of detecting finger movement is bulkier than initially desired. Due to the servo method of providing haptics, the resulting footprint is larger than necessary. Potentially in the future, electroactive polymers can be used instead. They harden when a current is applied, reducing the need for servos altogether. Meanwhile, on the end of our tool, current sensing units to monitor current applied on each actuator will allow for less components, as 4 sensors will not be required. It will also be more accurate in telling us how much torque is currently being applied on each motor. Finally, the potential to partner with other technologies in the market would allow this technology to be well fleshed out, pushing it further in the direction of being a real product.